Okay, so let's start. How many people notice that his wife actually disappears when the explosion happens? So, yeah. The other thing I want you to notice about this particular reaction, you might think, why do we not just use an excess of nitric acid in this reaction and have it all go at once? So we'll learn, probably not today, but probably on Friday, what's happening here and why each of these reactions gets successively a little bit more difficult to do. Okay? And this actually did make me realize how chemists, we often are trying to simplify things and we don't, because I can imagine how many people does that scare? Just looking at that scares me a little bit. Okay, so I understand that can be somewhat scary. We're going to try and simplify things a little bit. Sometimes I think we make diagrams to show how smart we are rather than to help make things simple. Okay, so and this was similar. Having said that, this is a great site to go and get some nice trivia about chemistry and where it might be useful. It has a lot of things like why asparagus makes your pee smell. They talk about that up there, so it's a good place. This is chapter 15. Chapter 15. Electrophilic Aromatic Substitution. Okay, so we already talked about the fact, and when we talked about aromaticity, that alkenes undergo addition reactions. Aromatic compounds do not. If we push them, because aromatic compounds are quite stable, we have to push them a little harder. And here we push it, and we'll see in a second how this pushes it by putting in this catalyst. We get substitution rather than addition. So let's recall, let's think about our aromatic compounds again. And remember that we have a lot of electron density inside the ring. The other thing I want you to remember is that even though we draw our reactions like this, we want to be aware that it's actually happening more like this. Remember, the benzene molecule is planar, and the electrophile's got to come in and it's got to get near that electron density, which is in the middle of the ring, and it will get, so the electrophile will approach from the top or the bottom of the ring, and then these pi electrons can reorganize and start to form a bond between the electrophile, and then we kick off just this is the anionic portion of the electrophile. We could also write this as an E plus and an A minus, or even just an E plus. So your electrophiles will come in many different forms. Sometimes it will be a cation, sometimes it will be a neutral molecule which is highly polarized and has a very electrophilic site. But these things are quite stable, so our electrophiles have to be quite reactive. Here, this is a little bit simpler than the last diagram. These are the reactions we're going to discuss probably today. The nice thing about all of these reactions is the main electrophilic aromatic substitution mechanism is the same for every one of them. And let's take a look at that. So, benzene is the nucleophile in these reactions, or the aromatic compound, and it's a crappy nucleophile, so we need a strong electrophile. It's crappy nucleophile because it's so stable, right? Remember, we talked about benzene being much more stable than we expected. And again, the electrophile must approach from above or below the ring plane. So the actual electrophilic aromatic substitution reaction, there's two steps. We get, in this, the nucleophile attacks the electrophile to form this thing. We call it, this is an arenium cation. Okay, and then the next step in the reaction, so the nucleophile attacks the electrophile. The next step in the reaction is just the removal of a proton from that intermediate. So this is just like a Bronsted acid base reaction. This is our base pulling off a proton, and that forms our substituted product. So the electrophile adds in the first step, and then the electrophile could go back, but our base comes along and removes a proton, thus giving us the substitution reaction. So that's why we have EAS, electrophilic aromatic substitution. We're using an electrophile to replace one of the protons on the aromatic ring. So we're substituting a proton for whatever our electrophile is. So this rhenium cation, it's a cyclohexadienyl cation, so it's somewhat stable, but it's certainly much less stable than the neutral aromatic compound from which it was formed. But it's somewhat stable because we can delocalize that positive charge over 3 different carbon atoms on the ring. And if we do some calculations, some high-level calculations, this is different rhenium ions, and it's just showing that the positive charge is actually spread out. These are very small negative numbers. We expect them to be very close to 0, and that's because of the resonance structures we can draw. We can draw 3 different resonance structures which show that positive charge getting spread around that ring. And those 3 resonance structures right here, right? We can just push our electrons to form this double bond and get the positive charge over here, continue to push them, and our positive charge gets spread around. So that's why resonance is so important, because it helps us to explain the stabilities of things and why we can get this delocalization of charge. In step 2, the rhenium cation acts as a Bronsted acid, and the proton on the carbon atom that became bonded to the electrophile, so that's the electrophile bonded to this carbon. It's bonded to 3 other carbons, but there's a proton left there. That proton is now quite acidic. It's very acidic. This thing really wants to give up its proton. So it's a strong acid. It can act like a strong acid, and even very weak bases. Remember, we're not typically in aqueous systems, although we can be, but we'll see in the next reaction where one of our products, it kind of looks like bromide is acting as a base, and bromide's not a particularly good base, although it is a pretty good base in quite nonpolar organic solvents. Then it doesn't want to be ionic, and so it will pick up a proton. So this step is just a Bronsted acid-base reaction, and our base pulls off the proton, the electrons that were in the carbon-proton bond, just reorganized to reform that carbon-carbon double bond, and this thing is aromatic again. So the first step, we broke the aromatic system, and the second step, we reestablish the aromaticity. We re-aromatize. So if we take a look at the energetics for this reaction, there's quite a bit of activation energy because we're breaking up an aromatic system, and we get this intermediate, which is going to be higher in energy. So this first step is very endothermic. This first step is very slow. Once this thing is formed, it can go back or it can go forward. The removal of the proton has a low activation barrier, and this is a very fast reaction, and it re-aromatizes. These reactions are typically exothermic, but they need not be. They're not really, typically they're not strongly exothermic reactions. They're close to thermoneutral. Sometimes they're endothermic. We can still make them go by heating the reactions. And we get useful yields for these things. So the first step is the rate determining step, and the second one is fast. So what we're seeing here, let's take a look at electrophilic aromatic substitution versus addition. This is the pathway we just took. It's, in this case, with this particular compound, this is bad too because we wouldn't use that catalyst, but I blatantly ripped this off of the internet, so we would use a FeBr3 as our catalyst. Anyway, this reaction is exothermic by about 11 kcals per mole, not hugely exothermic, but the addition reaction, if we were to go and add to the carbon-carbon double bond, we might expect to get a compound like this. This reaction would actually be endothermic. So this is exothermic, that's endothermic. This reaction is enthalpically driven because we prefer to form the exothermic reaction. We have to put energy in the other way. And the addition will always be higher in energy than the substitution product. So the reason for this is because in the addition reaction, we do not reform the aromatic ring. We've broken up the aromaticity. So because of that, the reaction would be endothermic. The substitution reaction ends up being pretty close to thermoneutral. Most often it's slightly exothermic because we re-aromatize. We regain that aromatic stabilization for the substitution reaction. Let's take a look at addition versus substitution for alkenes. And here we see that the addition reaction is somewhat favored. Both reactions are exothermic in this case. This is slightly exothermic, and this one is considerably more exothermic. And we really only need to go back to first year chemistry, and we can actually figure this out, what's going on. Well, in this reaction, we break a pi bond, and we break a weak bromine-bromine bond, and we form two strong carbon-bromine bonds. So this is quite exothermic. In this reaction, all we do is break our bromine-bromine bond and reform a hydrogen-bromine bond. So we don't gain a lot of energy there. We don't disrupt the pi system. It gets returned. So in this one, we break a weak bromine-bromine bond, and remember that pi bonds, breaking a pi bond takes less energy than breaking a sigma bond. Now, if we want to break the carbon-carbon bond completely, that is, rip the two carbons apart there, you have to break a pi bond and a sigma bond. But if we just disrupt the pi bond, it takes less energy than disrupting a sigma bond. So that's why in that reaction, the addition is favored. So let's take a look at a specific reaction. We can halogenate benzene by taking the halogen, Cl2 or Br2, in the presence of a catalyst. We typically use iron chloride if we want to do a chlorination, iron bromide if we want to, iron tribromide if we want to do a bromination. We also can use aluminum trichloride as the catalyst. It works as well. Aluminum tribromide is a bit of an exotic reagent and expensive, and we just wouldn't use it. This is cheap. Iron trichloride and aluminum trichloride are pretty similar in cost, and aluminum actually is a slightly better catalyst. So that's why we might use it. Both of these reactions go in decent yields, and our byproduct, our inorganic byproduct, is just the inorganic acid, the proton and the chloride. Let's take a look at what's going on. The first step in this is, remember we told you that bromine or chlorine by itself is not a good enough electrophile to react with the ring. So the purpose of the catalyst is to soup up the electrophilicity. It actually reacts, the first step, our halogen reacts with the catalyst to form a complex. Some people will also just show that it forms a bromonium ion, Br+, and Fe, Br4. That's fine. It is likely more of a complex. This is a Lewis acid-base complex, and it's very electrophilic now. So the first step is just souping up the electrophile, making it more reactive. Our halogen reacts with the catalyst to give us this souped up electrophile. That electrophile is now very reactive and can react with a crappy nucleophile like benzene. So the second step of the reaction then is the actual electrophilic aromatic substitution reaction. This souped up electrophile reacts with this crappy nucleophile to form our rhenium ion intermediate. And the other byproduct now is this thing, this FeBr4 with a negative charge on it. The second step is just the Bronsted acid-base reaction, and this is our base, and notice how it's a bit complicated. This is actually kind of entropically favored because we have two molecules coming together to form three molecules in this step. That gives us an additional reason for it to go forward rather than backwards. So now the lone pair of electrons just on the bromine just pulls off that proton. This re-aromatizes. At the same time, you break that iron-bromine bond, and you end up with your substituted aromatic, your inorganic halic acid, and you reform the catalyst. This catalyst is now available to go on and do more work. Okay? So catalysts are very good workhorses. We don't need a stoichiometric amount of this because it goes back. We only need a small amount. So that's it. I will tell you, and I think I say in the next slide, aromatic compounds are quite stable, so reactive electrophiles are needed. And in fact, from a mechanistic perspective, it is the formation of that electrophile, which often perplexes students mechanistically, okay? The electrophilic aromatic substitution is just a simple two-step reaction. It's always the same mechanism, but quite often there may be more than one or two steps to form whatever the real electrophile is that does the reaction. And we're going to see that in this reaction. This is an interesting reaction. We're doing a nitration reaction. We're adding NO2. We're substituting NO2 for one of the protons here. So you might think if we're substituting NO2, NO2 with a positive charge must be our electrophile, okay? Or some complex that delivers NO2 plus as our electrophile. So from this we can tell that this is, remember, an H plus came off, so this has to be an NO2 plus that went on. How do we make that? One of the things I like about this reaction, we all think of nitric acid as being a strong acid. It is a strong acid in an aqueous system, but in non-aqueous system, sulfuric acid is a much stronger acid. And the first step of the reaction, nitric acid is our base. And nitric acid acts as a base and removes a proton from sulfuric acid to give us this thing, which is just the protonated nitric acid. And notice now we can just throw water off. The second step is just the dehydration of that thing to give us water and this nitronium ion. Okay, this is a very powerful electrophile. It's not happy, it wants to find some electrons, form some sort of a bond, okay? So the first step is just an acid-base reaction with nitric acid as our base and sulfuric acid as our acid. So that's a nice concept there. It reminds you that just like water can act as an acid or a base, nitric acid can be an acid or a base if we have a strong enough acid. The next step then is just the dehydration. This is now our electrophile. It's a souped up electrophile that reacts with the aromatic ring to form our uranium ion intermediate. Now it's likely any base can come and remove this. I'm happy if you use any base. In this system, water is going to be the strongest base in this particular system. So typically we end up removing it and we get this, okay? I'm not going to be upset if you just say base or minus H plus or whatever. What I want you to know is that a proton is removed to re-aromatize. Something removes that proton. Another interesting reaction is sulfonation. Typically, we do this reaction, we use sulfuric acid and we bubble sulfur trioxide through it. Sulfur trioxide, some nasty stuff, but it reacts with sulfuric acid to form what becomes our electrophile. And again, we can tell what our electrophile is because this thing, if we just break this bond, this is going to be our electrophile, right? Okay. We can also do this reaction in concentrated sulfuric acid. This reaction is quite reversible, and that actually makes it useful synthetically. We can sometimes we do a reaction where we will sulfonate some aromatic compound that has other things on it, and when we sulfonate it, we block that position from other reactions. What we're also going to learn on Friday and next Monday is that once we start doing these reactions on substituted benzenes, they will go in specific places. So we can place this, then use it as a directing group to put something somewhere else and then remove it. It's been used for that quite often in the past, and it's a reversible reaction. Now, how would we do this? If we wanted to form this product, we make sure that we have as little water around as possible. If we want to go the other way, we throw some water in and we add some heat. You should always remember that.
I'm just a little confused with the first one. The hydrogen that comes on in the last step, does that come off from the...
We have the mechanism coming up next.
Okay.
Okay? So that's a good question, what's going on here. Okay? In here, we have lots of this around, and what happens is this is our acid, this is our base. Okay? So good question. And here's the answer. So the first step in fuming sulfuric acid, it's fuming because sulfur trioxide is a gas and it reacts pretty rapidly with water in the air, and as it's fuming out, that's why you see it fuming. So sulfur trioxide as a base removes a proton from the sulfuric acid and gives us this as our electrophile. This is the protonated sulfur trioxide. There's the conjugate base. That is a good electrophile. That's the electrophile that's actually attacked by the benzene acting as a nucleophile. This step is always the same. Once we form our electrophile, we get attacked by that crappy nucleophile. But because we have a very powerful electrophile, we form our rhenium ion intermediate. It gets deprotonated by something, and that gives us our electrophilic aromatic substitution product. Okay? So good question. This is under conditions where we are using fuming sulfuric acid. As I mentioned, we can also do the reaction in concentrated sulfuric acid, dry conditions, no water around. Now the reaction is very similar to the nitration reaction. What we have is what we call a disproportionation reaction. Just like water can react with itself, one water molecule acting as an acid, one water molecule acting as a base, the same thing can happen here. So one sulfuric acid acts as a base, removes a proton from another one, and we get this protonated sulfuric acid and the conjugate base. This thing can then kick off water, and there we go, we get the same electrophile that we had in the previous one. Okay, so under concentrated conditions, this is how we form that electrophile. Under sulfur trioxide fuming acid conditions, it's sulfur trioxide itself that gets protonated. This thing is the electrophile, and then the reaction is the same. Okay, so this is reversible. We control the reversibility by controlling the amount of water. If we want to go this way, we do this reaction under as dry conditions as possible. If we want to go the other way, we start with this and we have water. And typically what we do is we have a little bit of water and we bubble steam. That's how we heat the reaction. We use steam and we can do the reverse reaction. We also have to have sulfuric acid there for the reverse reaction to go. This is a useful reaction because now we're forming some carbon-carbon double bonds. How are we time-wise? Oh, great. So there's two types of Friedel-Crafts reaction which form carbon-carbon bonds. There's the alkylation reaction where we take some alkyl halide. We use, again, a Lewis acid catalyst to soup this up. So what is our electrophile? Our electrophile is going to be this thing, which is going to be a carbocation. Okay? Or it's something, a Lewis acid-base complex that delivers effectively a carbocation. And this is the same thing. This reaction is similar, except now we have an acid chloride as our electrophile. We soup it up with the same catalyst, and we get what we'll see in a minute we call an acylium cation, and that is our electrophile that adds to the ring. So note the similarity of the catalyst to that of the one used in halogenation, and the mechanism is actually somewhat the same. So let's take a look at this mechanistically. The first step in the reaction is the Lewis acid reacting with the alkyl halide. This is our Lewis base, and we get the formation of this complex, which is unstable, and it will actually, there's a lot of evidence that it actually does form a carbocation in the case of secondary cations and better. If we have a primary alkyl halide, it's probably this complex which is then reactive. It doesn't quite break up. But we've got a carbocation. That is our electrophile. Once we've formed our electrophile, it can just go ahead and do what electrophiles do, especially souped up electrophiles. They get attacked by a nucleophile. The pi electrons here form the carbon-carbon bond, and we get our rhenium cation, removal of the proton by this thing, and we get our product. We regenerate the catalyst, and we form the HCl. Okay? So this is very much the same. As it turns out, we can use anything that can give us a carbocation. For primary alkyl halides, the carbocation would be tightly associated with the Lewis acid catalyst, And as I say, even more likely, it's probably this complex, which is the electrophile. And then you could imagine that those are attacking the carbon, and then everything breaks up after that. We can use other sources of a carbocation. So if we take protein under decent acid conditions, HF will add to the double bond to give us the same carbocation that we just saw, and that carbocation can then get delivered to the aromatic group. Same with cyclohexene. If we protonate this, we end up with a carbocation. That carbocation just gets attacked by the nucleophilic benzene in both of these cases. These yields are not quite as good, but they're decent. The only thing I don't like about this reaction, I've only done 1 or 2 reactions with HF. I avoid them because that'll kill you, okay? So you will never do that reaction in an undergraduate lab. And there's actually antidote that you have to keep with you in case it... We had an accident in the lab and we were using fluorine and it smells a lot like chlorine, I'm told, and everybody just ran, so. Now for Friedel-Crafts reaction, it's kind of the same. There's a couple of differences. One, we have to heat these a little bit. One of the reasons is because the electrophile we're going to form is not as good an electrophile as a primary, secondary, tertiary carbocation. We're going to see in a second we form this thing called an acylium cation, which is pretty stable, so it's less reactive, and we have to heat it. The other thing, we need to use a full equivalent of the catalyst. It's still a catalyst, but we need to use a full equivalent. So let's take a look at that mechanism and see why that's the case. Now, in the box here, I'm just reminding you that we know how to make acid chlorides from carboxylic acids from a couple of chapters ago. So the first step in the reaction, very, very similar. Our acyl chloride reacts with the Lewis acid to form this thing. This thing now is fairly easy to break up because we get this acylium cation, and we can draw resonance structures. That charge is delocalized over the oxygen and the carbon. Which one of these is the more stable Lewis structure? Which one contributes more to the real structure? How many people think this one contributes more? Do you remember our rules? I should see more hands. Let's see more hands. Why is this a better contributor than this one? Full octets, right? This has a full octet, this has a full octet. In this one, we don't have an octet around that carbon, okay? Now, not a big deal, but it is just nice to know those things. And having said that, there are very general rules which the inorganic chemists, quite rightly, will dispute with us. So the organic chemists get a little hepped up on these, and if you take some of Dr. Ellis's classes, he'll talk to you why sometimes we go a little overboard. But not in this case. Okay, so this now is our electrophile, and this is the part that reacts. And we have our AlCl3. So the next step in the reaction is just the reaction of the electrophile with the nucleophilic aromatic compound to form our intermediate, same intermediate. Then we pull off the proton and form our product, HCl, and the aluminum trichloride. And remember, I told you that we had to use an equivalent. The reason is this is actually a decent Lewis base, and it will react with the Lewis acid to form this complex and just crashes out of solution. And that's what happens when we do this reaction. That's why we have to use a full equivalent of the catalyst, because it gets tied up in the end with the product. And then we work that up. This is the workup reaction. We have to work it up by just breaking up this Lewis acid-base complex with water to kind of release our product, and then we form the Lewis acid reacts with water to form this compound and HCl. So we need a full equivalent, hence the need for one equivalent of catalyst. We can also use anhydrides. So just like we could use other sources than the chloride for the alkyl compound, we can use other sources here. Typically, though, we need Lewis acids. We don't use Bronsted acids for these reactions. And this is just showing you how you form the acylium cation, same way. And then you get this, the acetate complexing with the Lewis acid, but that gives us the acylium ion. This thing is quite stable too, and at the end, acetic acid will be a byproduct because that's what will remove the proton. And then that will tie everything up, and you still have to work it up with water. Now, let's think about some limitations reactions. Hopefully, last semester in 2513, Dr. Lukeman or Professor Gillen told you that if a carbocation can rearrange to form a more stable carbocation, it probably will, right? And that's a limitation in these reactions. For the alkylation reactions, we see carbocation rearrangements all the time. So if we want to make this compound, one might think we would use this, but in fact, this is the minor product. What we get is this Lewis acid base complex. It's a primary carbocation, it's probably complex, but it just breaks apart to form this secondary carbocation. And then we end up getting this as the product because this cation is so much easier to form. So one of the limitations of the electrophilic aromatic substitutions, I should actually talk about, these are Friedel-Crafts limitations, and I'll fix that. Carbocation rearrangements are common, okay? So be aware. Also, big hint, there will be a rearrangement somewhere on a midterm or exam, okay? Another limitation, this isn't a limitation of all electrophilic aromatic substitution reactions, but particularly so with the Friedel-Crafts. Electron withdrawing groups, as we might expect, remember our benzene is our nucleophile. It's not a very good nucleophile. What do you think is going to happen to its nucleophilicity when we put an electron withdrawing group on it? It's going to suck that electron density away from the pi system, and it's not a very good electrophile anymore. So electron withdrawing groups deactivate the nucleophile. Okay, so for Friedel-Crafts reactions, this is important. These things aren't reactive enough when we go further. Now this is nice for the Friedel-Crafts acylations because they stop. One addition and then it stops. The next, the compound, which would be one of these, is too deactivated to react further, and it stops after the addition of one of the acyl groups. If we use something like ammonia, aniline, we can't do these reactions because these form a strong complex with the Lewis acid catalyst, and that actually ends up withdrawing a lot of electron density out of the ring, and these things are unreactive as well. So if the if there's substitution on the aromatic group and it can form a Lewis acid catalyst, it will deactivate it. Aryl and vinyl halides, these reactions don't happen, so these cannot be the source of our electrophiles. These reactions just don't happen. The cations are too unstable to form. If they did form, they would react very fast, but they just don't form. It's difficult to stop Friedel-Crafts alkylations at 1. Once we do the first alkylation, now we've put an electron donating group there. This is actually a better nucleophile than this is, okay? So initially we'll make this, but at some point the concentration of this gets significant and it's a better nucleophile. We start getting this as a byproduct, the second alkylation reaction. And in fact, in some reactions, we can even get 3 alkylations, depending on the reactions we're doing. So because alkyl groups are electron donating, they activate the aromatic compound, so it's better, the initial product is a better nucleophile than the initial reactant. And polyalkylation is common. Now, I've been very nice to you guys because we're going to end early again, but I'm going to give you a little problem I want you to think about now. And you can find the answer to this quite easily on the internet. So how would I make this? Starting from this, okay? We'll talk about this next class. We could do it now, but We're at a pretty good pace. The other thing I want to remind people, because this was a bit of a problem, I expect everybody to know what this arrow means, okay? What does that arrow mean? Yeah, it's retrosynthetic. It's really, all it's saying is, how do I make this from this, okay? So your reaction should be regular reaction arrows going back to here, or typically you can just go around and up. But that's what this means. It means, how do I make this compound from this? So that's it for today. We're going to solve this. Well, actually, we can do it now. We have lots of time. Anybody have any ideas how I would make this from this? So what's the problem? What would be the problem? Why can I not, why can I not just use that? Okay? So we're going to get a Lewis acid complex, but let's pretend we got a carbocation. Our carbocation would be this carbocation. What's this carbocation going to do? It's going to rearrange. It's going to quickly rearrange. This hydrogen atom is going to jump over to here, and we're going to get this carbocation. And then our product is going to be the T-butyl substituted compound, okay? So, we're smart people. Can we figure out what would we do, okay? So, what though if we use, I won't go through the mechanism, but if we use this, we will get this compound. Can we do anything there? What do we have to do to get from here to the compound that we're hoping to get? We're hoping to get this. Okay. What do we have to do? What kind of reaction goes from there to here? Is it a nucleophilic substitution reaction? Is it a reduction reaction? It's a reduction reaction, okay. As it turns out, we did talk about the Wolff-Kishner reduction last class. You could do that. There's a couple things you can do. The problem, what would the problem with this reaction be? It's not a big problem, actually. The problem is this ring, we don't want to reduce it. We don't want to hydrogenate it. We only want to hydrogenate this. As it turns out, that's not really that difficult, because we already know these things are quite stable. They're not easily reduced, and these things can be easily reduced. So there's a number of ways that we could, we want to reduce it completely, not to the alcohol, but to the CH2 group. And that's, we'll just talk about a couple of different reduction reactions that can do that.